Okay, so we're going to do a question that will use projections, orthogonal projections specifically. So you can see the question in front of you. We have a transformation from R4 to R4. We are on the real numbers. We have a space, we call it W, which is a span of two vectors, U1 and U2. U1 and U2 are presented to you right over here. Note very closely how U1 and U2 are built. Note, we will see this, but note that they are normalized. And even we will see that they are orthogonal to each other. Now we also have that TU1 equals U2 and that TU2 equals minus U1. The kernel of the transformation is the orthogonal complement of the space that is spanned by the two vectors U1 and U2, W. We are calling it W complement, orthogonal complement of W. All I want to do is just the first question. I want to find the transformation applied on the vector 1, 2, 3, and 4. What we are going to do is remember that if we take the orthogonal complement and orthogonal of a subspace and we add them together, this gives you a direct sum and it equals all the space. Therefore, we will be able to split this vector into a vector of W complement W and W. Unique split. Then we will find what should be the vector on W complement and on W and apply T to them and see what we've got and just add them as a result. So here is our vector V, let's call him, and here what I said, orthogonal decomposition of R4. So we can decompose the vector V into two components, W and W complement. W come from W subspace and W complement come from the subspace W complement. Therefore, we can say that TV, which this is exactly what we want to calculate, TV is equal to T of the sum of the two vectors that we created. Instead of V, we will write W plus W complement right over here. Therefore, because of linearity, additivity if you want, we can write it as TW and TW complement. Okay, don't forget that W complement, it is given to us that it's just the kernel of T. Therefore, when we apply the transformation to a vector in the kernel, we are just getting 0. So, what we've got is that TV equals TW plus something that equals 0. So we can say that TV is just T of W. W is the vector from W. But we have the base for W. It is spanned by the two vectors U1 and U2. We still don't know if it's a base because we don't know if they're linearly dependent. So let's see. And we will want to find the projection onto this. I will tell you this is a base. So it's much easier to work with an orthonormal base. So we'll check if this is an orthonormal base. And after we do that and get the orthonormal base, we will project the vector V onto this base to get the vector in W that we need and apply to this vector the transformation T, because we saw that TV equals exactly T applied on the vector from W. So let's project this V onto this space. So let's see how it goes. So we want to see if the span of W, what is it? Is it a base? Is it orthogonal? Is it orthonormal? Let's see. So we first check if it's a base. So let's check the norms. And when we calculate the norms, remember that it's just the inner product with itself, in this case the standard inner product in the Euclidean space, because it's with an inner product. So we get for the norms just one, so those are u1 and u2 are normalized vector. Their norm, their size is just 1. Now the dot product, the inner product between these two vectors, when we calculate it, we get 0. What does it mean? It means that these two vectors are orthogonal to each other by definition. This is exactly the definition for being orthogonal to each other. Okay, so what we've got, and remember that two orthogonal vectors are linear independent. So we got two vectors that span W, they are orthogonal to each other, linear independent, and they are normalized. So we can say that these two vectors are just orthonormal bases for W, so it will be much easier to project a vector onto an orthonormal base using Fourier coefficients. So if I want to project V onto W and get this little w that we are looking for, remember we want to calculate T of V, which we found that TW complement is 0, so we want TV equals TW. So we want to find W so that we will be able to apply T on this W to get the TV. So W is the projection of the vector V onto W, onto this orthonormal base. How we calculate the projection, the orthogonal projection of a vector into an orthonormal base? We are using the Fourier coefficients. We are taking the inner product between the vector we want to project V into the first vector base and multiply by the first vector base. And then we take again V inner product with u2 times u2. This is the projection. This is the projection of V onto the subspace W. This will give us this little w. Now we can calculate those coefficients. Remember that inner product gives us a scalar. So those are just coefficients for the vectors. So we will know what are the coefficients to get the orthogonal projection represented by these two vectors, by this linear combination of those two vectors. So let's calculate the inner product. We get 5 for u1 here and minus 2 for u2 right over here. Therefore, w equals 5 u1 minus 2 u2. Here it is. Now we can apply TV equals TW. W we said is equal this. Therefore, TV equals T of 5 u1 minus 2 u2. Now use linearity, homogeneity, and additivity, and you can take out the 5 and 2 and split this into two separate values. This is just linearity. Okay, now we know that TU1, we got that in the question, if you remember, TU1 equals U2 and TU2 equals minus U1. So we can use it now. So TU1 equals U2 and TU2 equals minus U1. Apply that. So instead of U1, we'll write here U2, TU1 equals U2. And instead of U2, TU2, we'll write minus U1. Here it is, minus U1. So we've got, take this to the left side, this to the right side, and got 2u1 plus 5u2. This is TV. This is the value we want to calculate. This is T of 1, 2, 3, 4. This is the factor we want to calculate. Here it is. Let's just open it. 2 times u1, we got, this is u1, multiplied by 2, plus 5 u2. Here it is. Calculate this. 2 times half is 1, 5 times half is 5 divided by, okay? Calculate it, and get the result. And this is the result. Here it is. This is the transformation applied on the vector we want to find. So this was a very nice exercise on orthogonal projection, working with orthogonal subspaces, working on a projection into a orthonormal base, looking if a span is built from orthonormal or from orthogonal and normalized vectors, looking on the norms and the inner product for orthogonality, and using the projection and understanding how to represent the vector. Thank you very much. And thank for Gemini for writing it down. Thank you for watching. If there are any mistakes or corrections, let me know. Thank you all very much. And this is it for this orthogonal exercise. Thank you all.